there, and welcome to Algebra 1 BCPS-TV style. My name is Laura Potter, and I'll be your host for today's episode. Before we start doing math, I want to tell you one of my favorite math jokes, but we're going to wait until the end to hear the answer. So here's the joke. What do you call a number that can't keep still? Think about it, and at the end of the episode, I'll share the answer with you. Let's begin today with a Think About It task. Today's Think About It task asks you to notice and to wonder about the graph of f of x, which is shown here on the left, and two different forms of the function that represent the graph of f of x, which are shown here on the right. What do you notice? What do you wonder? And now let's hear from my family to see what they noticed and what they wondered. As you listen, see if any of the things that they noticed were the same as what you noticed, and see if any of the things that you wondered were answered by my family. Hi, Spencer.
Hello.
So when you looked at the graph of f of x and the two different forms of f of x, what did you notice?
I noticed that if you expanded the x minus 1 squared, that expression, and distributed the negative, the functions are exactly the same.
So I'm looking up here at your work. So you expanded, distributed the negative 1. Oh, like combine like terms.
Yes.
So negative 1 plus 4 is 3.
Yeah.
So you noticed that not only did you notice, but you showed that those two functions were equivalent.
Yeah.
Okay, and what did you wonder?
I wondered if the simplified version can help us find the x-intercepts of the graph.
Why did you wonder that?
Okay, so if you factor this, can help us.
Hold on, we haven't learned factoring yet.
Oh, okay.
But that's coming up soon. So
Yay.
you gave everyone a preview of something that's coming in the future.
Okay.
Nice
You're
job.
welcome, guys.
High five. The material covered in today's mini lesson is the same as the print packet for Algebra 1 during the week of April 27th. This is Lesson 1. Our learning objective for today is to use the structure of a quadratic function written in vertex form in order to identify the vertex and sketch a graph of the function. If you remember back to our previous lesson, we looked at quadratic functions written in standard form. So today we're going to be looking at a new form of a quadratic function and see what that tells us about the key features of the function. And now let's learn about it. In this lesson, you're going to learn about a new form of a quadratic equation called vertex form. The vertex form of a quadratic function is f of x equals a times the quantity x minus h squared plus k. In a previous lesson, we talked about the form of a quadratic function called standard form. And if you recall, that was a function written in the form f of x equals ax squared plus bx plus c. So today we're adding a new form of a quadratic function to your tool belt so we can continue to get all of the information about the key features of the graph of a function. The a value of a quadratic function in vertex form identifies how the graph opens. It can either open up or open down, and it tells us if the vertex is a minimum or a maximum. That's the same information that the a value of a quadratic function written in standard form told us. Today, we're going to learn what the values of h and k tell us about the graph of a quadratic function. So let's begin with our first learn about it, which is example 1. In this example, we're going to make connections between the graph of h of x and the equation of h of x written in vertex form. I also have up at the top of your screen the general form of vertex form, which again is f of x equals a times the quantity x minus h squared plus k. Our goal is to help us figure out what the h and the k tell us about the graph of h of x. So the first thing that I'm going to do is I'm going to rewrite the equation for h of x in vertex form. Now you might be saying, well, Miss Potter, it looks just like it looks up at the top. What I want to do is make sure that all of my signs are also matching up. So there's an addition sign between the x plus 1 in the equation for h of x, and in the general form of vertex form, I see an x minus h. So we'll fix that up by using some properties of arithmetic. And then I also see that there's a subtract 5 in the equation for h of x, but in my vertex form equation, it's a plus k. So we'll fix that as well. So to do that, I'm going to begin by rewriting h of x. So I can keep the 2, And that's what my a value is, and we'll note that down here in a second. But instead of writing x plus 1, I'm going to write x minus negative 1. And that helps me to illuminate the fact that now I can tell what h is, and h is equal to negative 1. And I'm going to write, instead of minus 5, plus negative 5, or plus the opposite of 5. So now I can identify my values. So when I look, my value of a is 2. My value of h is negative 1. And my value of k is negative 5. So let's see, h is negative 1 and k is negative 5. So if I look on the graph, I can see that, oops, wrong green, that negative 1, negative 5 are the values for my vertex. So that's what the values of h and k tell us. So now let's fill in the rest of my table. So I can see that the graph opens up because I can see that, but also because a is positive. There is also a minimum value. My minimum value is y is equal to negative 5. And my vertex is negative 1, negative 5. Let me get that comma in there. And I can see that from the graph, but now I can also see that from the equation of h of x written in vertex form. So my vertex is negative 1, negative 5, which is the same as the h value and the k value. It's really important to remember, though, that I cannot pull the h and the k values from the equation of the function in vertex form unless it matches with the equation for vertex form. So that's why we had to do a little bit of manipulating here in this first step. The last thing that I want to identify is the axis of symmetry. So first I'm going to draw that on my graph of h of x. Let me draw the line for the axis of symmetry. So that happens right here along the line x equals negative 1, which is the same as x equals h. So it's really great that we can now take a look at the equation of a quadratic function in vertex form and not only identify the vertex, but we can also identify the axis of symmetry. And if we put together the information about how the graph opens up, we can tell if the vertex is a minimum or a maximum. So we're starting to build a repertoire of tools that we can use to identify all of the key features of a graph of a quadratic function without actually having the graph there to help us. In your print packet, there's another example connecting the graph of a function with its equation in vertex form. So make sure you check that out. Now we're going to move on to another example where we're going to make a connection between the graph of the function, in this case, the graph of h of x, vertex form, and standard form. So sometimes we're given an equation written in vertex form and we want to convert it to standard form. Why would we want to do that, you ask? Well, standard form provides us some information about the graph, specifically how the graph opens, but vertex form also tells us that, but it also tells us the y-intercept. So if I was provided with an equation in vertex form and I wanted to know the y-intercept, I would need to convert that equation into standard form so I could identify the value of c, which is the vertex. So let me show you what that looks like with our specific example of h of x. So I have h of x written as a function in vertex form. So h of x is equal to 2 times the quantity x plus 1 squared minus 5. And I want to convert that to standard form. So what I'm going to do is I'm going to use multiplication. So this becomes the quantity x plus 1 squared means x plus 1 times x plus 1 minus 5. Now, if you recall, we learned how to perform multiplication by using a box method. So I have x plus 1 and x plus 1, and I'm going to multiply the corresponding rows and columns together. So I have x squared, x, x, and 1. So I'm going to combine like terms. So h of x becomes 2 times the quantity x squared plus 2x plus 1, minus 5. Now I'm going to distribute the 2. So I have 2x squared plus 4x plus 2 minus 5. And my last step is to combine like terms. So I have, and the like terms are 2 and negative 5. So I have 2x squared plus 4x minus 3. So what's great about this is that my a values are the same. So my a value in vertex form is the same as my a value in standard form. So my a value is 2, and that is going to tell me that my graph is opening up and that the vertex is a minimum. My b value is 4, and my c value is negative 3. And remember, the value of c tells us the y-intercept as an ordered pair, and if I look over here at the graph of h of x, I can feel good about my work because the y-intercept is in fact 0, negative 3. So the last thing that we're going to do is take a look at what happens if you're given the equation of a quadratic function in standard form and you want to know the vertex. We don't know yet how to manipulate an equation in standard form to move it back to vertex form, but we do have a formula that can help us. To find the vertex of a quadratic function when it's written in standard form, we're going to use the formula x equals the opposite of b divided by 2a. And that's going to give us the x-coordinate of our vertex. So in this particular example, I will rewrite the opposite of b, which is the opposite of 4, divided by 2 times a, and my a value was 2. So this becomes negative 4 divided by 4, which is negative 1. So the x-coordinate of my vertex is negative 1. The other thing that I need to do to find my vertex is to find the y-coordinate. And to do that, I'm just going to evaluate the function h of x in standard form, because remember, all of this work we're doing when we have an equation written in standard form. So I'm going to evaluate h of negative 1. That means everywhere where there is an x, I'm going to replace that with a negative 1. So I have 2 times negative 1 squared plus 4 times negative 1 minus 3. So I'll start and apply my exponent. So negative 1 squared is 1. 2 times 1 is 2. So 2 plus 4 times negative 1 is negative 4 minus 3. 2 plus negative 4 is negative 2, and negative 2 minus 3 is negative 5. So h of negative 1 equals negative 5. And I'm feeling really good about the value that I found for my vertex because that's actually what is shown on my graph. Nice job. There's another example in your print packet showing how to convert from vertex form to standard form, which is what we did in the top portion of this example, and then how to find the vertex of a quadratic function if you're only provided the function in standard form. So make sure you check that out before you do the try it and the show what you know problem. Today, our first learning objective was to use the structure of a quadratic function written in vertex form to identify the vertex and sketch a graph of the function. In your print packet, there's a graphic organizer that summarizes the new learning for today. Use that along with the completed examples to get creative in the Try It section. You get to create your own equations and identify the vertex. Don't forget, there are some sample answers in the back of your print packet. Before we move into our second learning objective, let's switch gears with another Think About It task. What is alike and what is different between the two sets of graphs? Use the next few seconds to figure out what you see that is alike and different. As you listen to what my family has to say, see if you can add to what you think is alike and different. Hi, Lily.
Hi.
How are you?
Good.
What do you notice that is alike and what do you notice that is different about the two pictures that are on the screen?
Something alike that I noticed is, well, they both have two parabolas opening up, and something different that I noticed is one graph has a parabola right to the red, and one has a parabola left to the red parabola.
So you're saying that the blue parabola is to the right of the red parabola?
Yes.
And the green parabola is to the left of the red parabola?
Yes.
Thank you, Lily.
You're welcome.
The material covered in our second learning objective is the same as the Algebra 1 print packet for the week of April 27th. This is lesson 2. Today, we will replace f of x with f of x plus k times f of x, and f of x plus k with specific values of k in order to identify the transformation or the changes to the graph of a quadratic function. In this lesson, we're going to transform quadratic functions, meaning we're going to move them around and shift and maybe stretch or shrink the graphs of the quadratic functions. The transformations are going to be described by comparing equations, graphs, and tables of two functions. The parent function, which is f of x equals x squared, and that's always going to be shown in red with a dotted graph, and it will be labeled, and the transform graph, which will be blue, and it's also going to be labeled as g of x. We're going to be looking at our transform functions in vertex form to see how those values change the way the graph looks. The different transformations that we're going to look at are vertical stretches, vertical compressions, reflections, vertical translations, and horizontal translations. For each of the different transformations that I showed you on the previous screen, I'm going to pull up an interactive Desmos graph so that we can see what those transformations look like from an equation perspective, a graph perspective, and a table perspective. The first transformation that we're going to look at is what's called a vertical compression. I want to share with you some information that will be true, though, about each of our transformations. The red graph of f of x, which is the dotted red curve, is our parent function, and it's always going to be represented by a red dotted curve. The transform graph, or the transform function, g of x, is always going to be represented by a blue solid curve, and we're going to be changing that value so that we can see the effect on the graph of g of x compared to the graph of f of x. So let's start by looking to see what happens when I change the value of a so that it is between 0 and 1. So what you might be noticing is that if the value of a is anywhere between 0 and 1, the graph of g of x is wider than the graph of f of x. The next transformation we're going to look at is what is called a vertical stretch. The graph of f of x is a red dotted curve, and the graph of g of x, our transform function, is a blue solid curve. This time, I'm going to be looking at what happens when my value of a is greater than 1. So let's take a look. You might be noticing that as I make a larger and larger, the graph of g of x becomes narrower than the graph of f of x. The next type of transformation that we're going to look at is a reflection, and reflections that also contain a vertical compression or a vertical stretch. So this time I'm going to be changing the value of a in my transform function to be negative. So let's take a look and see what happens as I move the slider from 0 to negative 18. So when I start, it looks like my graph is reflected over the x-axis and it's really, really wide until I get to a is equal to negative 1. And when I get to a is equal to negative 1, let me put that in there, the graph is reflected right across the line y equals 0, or right across the x-axis. So now let's take a look and see what happens as I move my, my slider towards more negative values. And so it appears that in addition to being reflected, my graph is getting skinnier and skinnier, or there's a vertical stretch. My next transformation is called a vertical translation. So right now, you can see that the transformed graph, g of x, is in the form x squared plus k. This time, I'm going to be changing the value of k. So first, I'll move k from k equals 0 in the positive direction. So make note of what's happening to the blue graph compared to the red graph. It looks like the graph is shifting up, and it's shifting up exactly k units from the parent function. So now let's take a look and see what happens when k is negative. So here's what happens when k is negative. So k is, if the value of k is negative, it's shifting the graph down from the graph of f of x. The last type of transformation we're going to look at is what is called a horizontal translation. And that's a translation in its equation form, the quantity x minus h squared. So we're going to be changing the value of h and see what happens to the graph. So right now my value is h equals 0. So f of x and g of x are actually the same exact graph. So let's see what happens when h is positive. The graph is moving to the right. And now let's see what happens when h is negative. The graph is moving to the left. For each of the transformations that we looked at using the Desmos graph, there's also a graphic organizer in your print packet to help you understand the information. So in addition to the name of the type of transformation up at the top, there's an example on the left. And in the center, there's a picture of the graph and a picture of the table. And on the right, there's some information about how the graph of g of x looks compared to the graph of f of x. And there's also an explanation about the particular example that's on the left-hand side. So we have vertical stretch, there's a vertical compression, a reflection, and then we have vertical translation and horizontal translation. Now, the only thing that I want to, let me see if I can get this all on one page. The only thing that I want to bring to your attention about horizontal translations is that sometimes it's necessary to rewrite the function so that I can know exactly what the value of h is. So in this example, g of x was the quantity x plus 4 squared. But if you remember, I was looking at the transformation in the form the quantity x minus h squared. So I had to rewrite my function as g of x equals x minus negative 4 quantity squared so that I could see that h was negative and it moved the graph to the left. So in the Desmos activity and the notes section, we learned about different types of transformations that can happen to quadratic functions. In addition to a single transformation, transformations can be combined. And there are 2 additional examples in your print packet to show what that looks like. We're not going to go over those examples, but I encourage you to read through examples 8 and 9 in your print packet so you can see exactly what's happening when more than one transformation is applied. Today, we spent some time changing the values of k to figure out how the graph of a quadratic function transformed. We replaced f of x with f of x plus k. That was a vertical translation. K times f of x. That was a vertical compression and a vertical stretch, as well as a reflection. And f of x plus k, that was the horizontal translation. And now it's your turn to try some of the problems in your print packet. Before you get started, make sure you spend a few minutes analyzing the equation and identify the different transformations that occurred based on the equation. Use the examples in your print packet to help you organize your thinking. Don't forget, there's an answer key at the end of your print packet. All right, I promised we would get back to this joke. So if you remember back to the beginning, my joke was, what do you call a number that can't keep still? Roman numerals. Thank you for tuning in today to learn some math. You should be ready to work on the try it problems and the show what you know problems in your print packet. Applying what you learned is so important to solidifying your understanding. See you next time.